NENOMATICA, where mathematics meets YouTube excellence. Welcome to our comprehensive exploration of cubic expressions and equations. In this video, we'll introduce you to the fascinating world of cubic polynomials, their properties, and methods for solving cubic equations. We'll cover 4 main chapters in our study of cubic expressions. Chapter 1, Solving cubic equations in special cases. Chapter 2, Analysis of the number and signs of the roots of a cubic equation. Chapter 3, Solving incomplete cubic equations. And Chapter 4, Relations between coefficients and roots of a cubic equation. Let's begin with Chapter 1, Solving cubic equations in special cases. Today, we're going to explore a special case for solving cubic equations when the sum of the coefficients equals 0. Let's start by looking at the general form of a cubic equation, which is ax cubed plus bx squared plus cx plus d equals 0, where a, b, c, and d are real numbers and is not equal to 0. Now, let's examine a special case of cubic equations. If the sum of all coefficients is 0, then x equals 1 is a solution to the equation. This means if a plus b plus c plus d equals 0, then x equals 1 is a solution to the equation ax cubed plus bx squared plus cx plus d equals 0. Let's prove this theorem. If we divide the cubic equation by x minus 1, we should get a quadratic equation. If the division works without a remainder, then x equals 1 is a root of the cubic equation. First, let's use the condition that the sum of coefficients is 0. This means that a plus b plus c plus d equals 0, which we can rearrange to d equals negative a minus b minus c. Now let's substitute this value of d back into our cubic equation. We get ax cubed plus bx squared plus cx plus negative a minus b minus c equals 0. Let's rearrange this equation to group like terms. We get ax cubed plus bx squared plus cx minus a minus b minus c equals 0. Now we can rewrite this as ax cubed minus a plus bx squared minus b plus cx minus c equals 0. This allows us to factor out common terms. Let's factor out the common terms from each parenthesis. We get a times x cubed minus 1 plus b times x squared minus 1 plus c times x minus 1 equals 0. We can further simplify x cubed minus 1 as x cubed minus 1 cubed, which factors as x minus 1 times x squared plus x plus 1. Similarly, x squared minus 1 factors as x minus 1 times x plus 1. Notice that x minus 1 is a common factor in all terms, so we can factor it out to get x minus 1 times a times x squared plus x plus 1 plus b times x plus 1 plus c equals 0. Now, we have factored the cubic equation into the product of x minus 1 and a quadratic expression. If we expand the quadratic part, we get x minus 1 times ax squared plus ax plus a plus bx plus b plus c equals 0. Let's collect like terms in the quadratic expression. We get x minus 1 times ax squared plus ax plus bx plus a plus b plus c equals 0, which simplifies to x minus 1 times ax squared plus x times a plus b plus c equals 0. This proves that x minus 1 is a factor of the cubic equation when a plus b plus c plus d equals 0, which means x equals 1 is a solution to the equation ax cubed plus bx squared plus cx plus d equals 0 when the sum of the coefficients is 0. It's worth noting that there's also a direct way to verify this result without the factorization approach. We can simply substitute x equals 1 into the cubic equation and check if it gives us 0. Let's see the direct verification. If we substitute x equals 1 into the cubic equation, ax cubed plus bx squared plus cx plus d, we get a times 1 cubed plus b times 1 squared plus c times 1 plus d, which simplifies to a plus b plus c plus d. Since we know that a plus b plus c plus d equals 0, this confirms that x equals 1 is indeed a solution. And finally, without the division process, we can also find the quadratic formula directly. When we factor x minus 1 out of the cubic equation, the remaining quadratic part is ax squared plus a plus b x plus a plus b plus c, as we derived earlier. To summarize, we've proven an important theorem. If the sum of the coefficients in a cubic equation ax cubed plus bx squared plus cx plus d equals 0 is 0, then x equals 1 is a solution to the equation. This is a useful property that can help simplify the process of solving certain cubic equations. Let's look at an example to apply this theorem. Consider the cubic equation 2x cubed minus 5x squared plus 7x minus 4 equals 0. Let's check if the sum of coefficients is 0. 2 minus 5 plus 7 minus 4 equals 0. Since the sum is 0, we know immediately that x equals 1 is a solution. This makes solving the cubic equation much easier, as we can factor it as x minus 1 times a quadratic expression, and then solve the quadratic to find the other two roots. This theorem is just one of many special cases in polynomial equations that can help us find solutions more easily. Remember, mathematical patterns and properties like this one can significantly simplify complex problems. Let's find the roots of the following cubic equation: x cubed minus 6x squared plus 11x minus 6 equals 0. We can observe that this is a third-degree polynomial, and we'll use a special method to solve it. The first step is to check if the sum of the coefficients equals 0. Let's add them up. We have 1 from x cubed, negative 6 from negative 6x squared, 11 from 11x, and negative 6 from negative 6. So we have 1 plus negative 6 plus 11 plus negative 6, which equals 0. This confirms that we can use our special method for solving this cubic equation. Now, let's use the special formula for cubic equations where the sum of coefficients is 0. According to this rule, we can rewrite our cubic equation in the following factored form: x minus 1 times quantity x squared plus quantity a plus b times x plus quantity a plus b plus c equals 0, where a, b, c, and d are the coefficients of our original equation. Let's substitute our coefficients into this formula. We have it equals 1, b equals negative 6, c equals 11, and d equals negative 6. So our equation becomes x minus 1 times the quantity x squared plus the quantity 1 plus negative 6 times x plus the quantity 1 plus negative 6 plus 11. Let's simplify x minus 1 times the quantity x squared plus negative 5, x plus 6 equals 0. Now, we have a product of two factors, x minus 1, and a quadratic expression. For this equation to equal 0, either x minus 1 equals 0, or the quadratic expression equals 0. From the first factor, we get x equals 1 as our first root. For the second factor, we need to solve the quadratic equation x squared minus 5x plus 6 equals 0. We can factor this as x squared minus 5x plus 6 equals quantity x minus 2 times quantity x minus 3 equals 0. From the factor quadratic, we get two more roots: x equals 2 and x equals 3. Therefore, the three roots of our original cubic equation are x equals 1, x equals 2, and x equals 3. Let's verify our answer by substituting these values back into the original equation. Let's verify our solution by checking if x equals 1 satisfies our original equation. When we substitute x equals 1 into x cubed minus 6x squared plus 11x minus 6, we get 1 cubed minus 6 times 1 squared plus 11 times 1 minus 6. That's 1 minus 6 plus 11 minus 6, which equals 0. Similarly, you can verify that x equals 2 and x equals 3 also satisfy our original equation. In summary, we've learned a special method for solving cubic equations when the sum of the coefficients equals 0. This method allows us to find one root immediately as x equals 1, and then we only need to solve a quadratic equation to find the remaining two roots. Remember, this method works specifically when the sum of all coefficients in the cubic equation equals 0. In such cases, we can directly apply the factorization x minus 1 times a quadratic expression. This method is much faster than polynomial division or using the cubic formula. Let's look at the equation we need to solve. Our example problem is the cubic equation x cubed minus 4x squared plus 5x minus 2 equals 0. According to the approach shown in our method, let's first check if the sum of the coefficients equals 0. We have 1 plus negative 4 plus 5 plus negative 2. That equals 0. This means we can use a special factorization method. Now, since the sum of coefficients is 0, we can apply a special factorization formula. According to our method, we can express the cubic equation in the form x minus 1 times the quantity x squared plus a plus b x plus a plus b plus c equals 0. Let's identify the values in our equation, where is 1, b is -4, c is 5, and d is -2. Let's simplify this expression. Inside the brackets, we have 1x squared plus 1 plus -4, which gives us -3x, plus 1 plus -4 plus 5, which equals 2. So our factorized equation becomes x minus 1 times the quantity x squared minus 3x plus 2 equals 0. Now we need to set each factor equal to 0 and solve for x. For the first factor, we have x minus 1 equals 0, which gives us x equals 1. For the second factor, we need to solve x squared minus 3x plus 2 equals 0. We can factor this quadratic expression as x squared minus 3x plus 2 equals x minus 1 times x minus 2, which equals 0. So we get x equals 1 or x equals 2. Let's combine all our solutions. We found that x equals 1 from the first factor, and x equals 1 or x equals 2 from the second factor. Since x equals 1 appears twice, we have the solution set consisting of x equals 1 and x equals 2. So our final answer is that x equals 1 or x equals 2. Let's verify our solutions by substituting them back into the original equation. Our original equation was x cubed minus 4x squared plus 5x minus 2 equals 0. Let's substitute x equals 1. 1 cubed minus 4 times 1 squared plus 5 times 1 minus 2. That's 1 minus 4 plus 5 minus 2, which equals 0. So x equals 1 is indeed a solution. Now let's substitute x equals 2. 2 cubed minus 4 times 2 squared plus 5 times 2 minus 2. That's 8 minus 16 plus 10 minus 2, which equals 0. So x equals 2 is also a solution. Both solutions check out, so the complete solution set for this cubic equation is x equals 1 or x equals 2. Let's summarize what we've learned in this video. First, we identified that the sum of the coefficients in our cubic equation was 0, which allowed us to use a special factorization method. Second, we applied the factorization formula to express our cubic equation as a product of two factors x minus 1 and a quadratic expression. Third, we solved each factor separately, finding that x equals 1 is a solution from the first factor, and x equals 1 or x equals 2 are solutions from the second factor. Finally, we verified that both x equals 1 and x equals 2 satisfy the original equation. This method is very useful when the sum of coefficients in a cubic equation equals 0, as it allows us to quickly factor the equation without using more complex techniques. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.